Okay, so make sure this works. Okay. Okay, so last time we were talking about unsymmetrical faults. I will try to wrap that up so we can move on to one last topic. And we did the single line to ground fault. I think we stopped here last time, right? So we stopped at the single line to ground fault. We said that, for every type, so we will talk about three main types of faults. So single line to ground fault, line to line fault, and line to line to ground fault. Okay, because any of the three-phase faults are balanced. So if they are balanced, we do a single phase equivalent circuit, or you do the positive, or you only worry about the positive sequence network in these sequence circuits, right? So that's okay. So what we did last time was, okay, we said that for the single line to ground fault, or for all the types of faults, we will start with a couple of assumptions, and then a couple of sort of facts about the circuit, and we will use these facts by manipulate these facts, which are a set of equations, and move them into the sequence domain, and we will end up with sort of a few other facts that we will utilize to figure out how to connect our sequence circuits. That's the process, right? So for the single line to ground fault, we have three phases here, and we have one of the phases is now connected to ground through an impedance ZF, right? Assuming that phase is A, one of the assumptions that we said we will use at the beginning of this chapter is that if the phases do not have a fault on them, we will assume that their currents are zero. So IB is 0 and IC are 0, right? So IB and IC are 0, and IA will carry the fault current. So the fault current will move from phase A through the ground back through the neutral of the connection, the star connection. So if I would like to calculate the voltage across phase A, VA to ground, it is equal to the current flowing from phase A into the fault impedance. This fault impedance can be 0, can be large, can be small, right? Whatever it is, it's a fault impedance, yeah. So, and these are the two conditions that I have. IB equals IT equals 0. This is one of the conditions. The other condition is VAG, the voltage between phase A and ground, is equal to Z fault times IA. So we started with these conditions last time, and then we sort of converted these phase domain phase domain quantities into sequence domain. When we did the conversion to sequence domain, so we just took the A, IA, and 0, 0, the currents are IA, and 0, 0 for B and C, converted them to sequence quantities, and then did the same thing for VAG, converted the phase A voltage to its sequence representation, converted the phase A current to its sequence representation, and we did some simplifications. So this was the sequence representation of phase A current, sequence representation of phase A voltage, and multiplied by ZF. And we substituted with what we know about the sequence currents. So the sequence currents, when you convert IA and Z and 0 and 0 to sequence quantities, we ended up with 1/3 IA, 1/3 IA, 1/3 IA. So we substituted with 1/3 IA for each of these, and we ended up with two conditions. One condition is I0, the zero sequence current, the positive sequence current, negative sequence current are all equal, and they're equal to 1/3 IA. That's from here. And then V0 plus V1, the summation of the positive, negative, and zero sequence voltages is equal to, since these three currents are the same, we can rewrite this as 3ZF times I1. Since the positive, negative, and zero sequence currents are all the same, I can just write it as 3 times the positive sequence current times ZF. I just grouped 3 and ZF together just because it's more convenient, because when we look at our circuit will have the positive sequence current flowing. So I can put 3ZF here, and it's the same. It's just a mathematical representation, right? So what do these two conditions tell us? These two conditions tell us that all the currents are equal. All the sequence currents are equal, which means that I can put them all in series, the circuits in series. And the summation of the sequence voltages is equal to the voltage drop across an impedance equal to 3ZF, with current I1 or I2 or I0 flowing through it. So the summation of the sequence voltages 1, 2, and 3 is equal to the voltage drop across this impedance, 3ZF. Right? So these are the conditions. So then the next step is no problem. The next step is, okay, what is the value of the sequence current? You take this voltage divided by the impedance in this, the series impedance in the circuit. And then you have your values for I1, I0, I2, V1, V0, and V2, etc., etc. Right? So any questions on this? We did this last time, so it should be reviewed. But what we'll do next is exactly the same, actually, for the different types of faults. We will start with, you always have to draw the Thevenin equivalent circuit, the Thevenin equivalent sequence circuits at the specific bus where the fault is occurring. You draw 3 circuits, and then you figure out how to connect them based on the type of fault. Right? That is the sequence of operation. I will not go through this. So this is an example this is an example. So they repeat what we were just saying. So they have, they have the 3 sequence circuits, right, over here, and they were told calculate the subtransient fault current in per unit and in kiloamps, so in per unit and in actual values, for a bolted single line to ground short circuit. Bolted single line to ground short circuit means the impedance, the fault impedance is equal to 0. Right? There's no impedance to ground. The fault impedance is equal to 0. That's what this means. So that's why 3ZF goes away. Right? So 3ZF is 0 when I say bolted. Yeah. So they want the per unit fault current, actual value of the fault current. Yeah. For this single line to ground short circuit. As soon as I tell you single line to ground short circuit, you take your 3 sequence circuits, connect them in a certain way. Right? And if they tell you bolted, you put 3ZF equal to 0. And then you just, then you calculate then you will calculate the current. The current in the circuit is equal to this voltage divided by the 3 impedances that are in the circuit. That's the current I1, it's also the current I0, it's also the current I2. Right? So now you have your sequence currents. Then you also need to calculate your sequence voltages. Right? We said that the sequence voltage, this voltage is equal to this voltage plus this voltage are equal to 0, right? So, because current is flowing in this direction, I2, all the currents are flowing out of the circuits, right? So, V2 plus this voltage drop are equal to 0. So, V2 is equal to the negative of this voltage drop. V1 plus this voltage drop minus this voltage drop are equal to 0. And you calculate V1 from there. Same thing with this. V0 is equal to minus this voltage drop. Right? That's what they did here. So they first calculated the currents, which is equal to the voltage divided by the sum of the impedances. They calculated that in per unit. And then 1.28. So then they converted the sequence quantities, since I know that from here I0 is equal to 1/3 IA. So if I want to calculate IA, I take the sequence quantities and multiply by 3. 3 times the sequence quantity is equal to the IA, the phase A current. Right? So that's what they did here. Right? 3 times the sequence quantity, which was this, is equal to the IA current. Fine. They went back to the system and they had the base current value of a certain value here, right? So this is where chapter 3 comes into play, right? That's why this exam, if I test you on this material, it has to be cumulative because of this, right? Because if I tell you find the actual value, right, then it's all chapter 3 material considered. Right, so then they had a base current in a certain region of certain value at bus 2, so they multiplied the value of the current, the phase A current, at this bus, right? So this was the per unit value sequence, and this is per unit value phase, and they converted that to actual value phase currents, okay, by multiplying by the base. And then they calculated we want to calculate the sequence voltages, so we can calculate the phase voltages from there. The sequence voltages, as we said, right? It's looking at the circuit. So V0 is equal to negative of the voltage drop across the zero sequence impedance. V1 and V2, as we discussed. So we have the three sequence voltages here. Then you can take your three sequence voltages, multiply by the sequence matrix, convert them to phase quantities. Any questions on this? No? It's straightforward. Yeah, it's hopefully it's straightforward. So that was the single line to ground fault, right? The line to line fault and line to ground fault, exactly the same process. Okay, so I will not go through the proof. I will just say, okay, here we have, because you have these circuits, the connections between these circuits are available on your equation sheet, right? So our conditions, let's make sure we understand the conditions. So the line to line fault, meaning we have two lines touching each other. That is a type of fault. They're not touching the ground. If two lines are touching each other, let's say they are lines phases B and C. That means the current is flowing from phase A into from phase B into phase C, and phase A doesn't have a fault on it. So we will assume that there's, that current is much lower or zero, right? So we will assume that phase A current is zero. Phase B and phase C currents are opposite of each other, right? Since the phases are touching each other, so current will go from one phase and come back from the other phase. That's how the fault current will flow. And then if there happens to be an impedance, so let's say there's a tree that fell between phases A and B, or phases B and C. This tree will have an impedance, right? So that will be the fault impedance. So the voltage across that fault impedance is equal to the voltage between phases B and C, or the line voltage B and C, basically, in this case, right? So that voltage is across that fault impedance. And you can use, okay, what current is flowing through that impedance? You can either use the phase B current or the phase C current, but with an opposite sign, right? Does not matter here. So what they have here is, the voltage across the fault is the phase B minus VBC, right? That's VB to ground minus VC to ground. And that is equal to the fault impedance multiplied by the fault current, right? So these are our inputs, right? We will take those and do the same, convert them to sequence quantities, and then, yes, sir.
For the previous single line to ground,
Yeah.
We assume that IA and IB are 0.
No, we assume that IB and IC are 0.
Okay.
We had the fault on phase A, but it doesn't matter. If you assume that the fault was on phase B, you have to assume IA and IC are 0, and you rewrite these equations, right? But
No, but then in the matrices when we
yeah.
can I keep going down? I think in the we found out the phase A current.
Yes.
But we also replicated that for B and C. I think.
Where? In the example?
Yeah. Yeah, right there. When we find the voltages equal.
Yeah, we didn't. We only found phase A current.
And then the next line, what's on the rightmost?
No, these are the sequence currents. These are the sequence currents, right? These are the sequence voltages. How do you calculate the sequence voltages from the sequence circuits? You multiply the sequence current by the sequence impedance, right?
Okay, so they're sequence currents.
Yeah, no, these are sequence currents. This is V0. How do you calculate V0? V0 is equal to then V0 plus this voltage drop are equal to 0. So V0 is equal to the sequence current negative of the sequence current, right? Because sequence current is flowing in the opposite direction. So negative of the sequence current times the sequence impedance. So here, V0 is equal to negative 0 minus, or negative of the sequence current. Sequence current was what? Here, minus J 1.9 blah blah blah, right? So it's negative of the sequence, negative here, of the sequence current multiplied by the sequence impedance. Right? It's negative the sequence current multiplied by the sequence impedance. Because the polarity, you have to maintain the polarities. It's okay? No, we didn't use... Okay, for line-to-line fault. Again, here the assumption would be IA is 0, IB and IC are opposite of each other. The voltage that's across the fault impedance is the VBC line voltage. Right? And that's what these conditions tell us. Then we can go through and convert everything to sequence quantities and do some simplifications. Then the output of that will be a set of equations, in this case 2 equations, that will define how the circuit is connected. So here, the output of that was I0, the zero sequence current is equal to 0. The positive and negative sequence currents are equal and opposite of each other. And the third condition is the difference between the positive and negative sequence voltages is placed across the fault impedance. So how do you construct a circuit based on this? If I tell you I0 is equal to 0, so I have my 3 sequence circuits. This is my 0 sequence circuit. This is my positive sequence circuit, and this is my negative sequence circuit. They will always look like this, right? Like these are the Thevenin equivalent circuits for the sequence circuits, for your sequence representation of the system at the faulted bus. So you have a system that has a fault at bus 2. You first draw the sequence representation of the system, positive, negative, and 0, the full system. Then you go to the bus where the fault is occurring, and you find the Thevenin equivalent circuit from this bus. You will end up with 3 circuits that will always look like this. The 3 circuits will always look like this, right? It's just the values that you put in there will be different, right? And then if they tell you it's a balanced 3-phase fault or a 3-phase fault to ground, all you need to worry about is the positive sequence circuit. Put the fault here. If they tell you the fault impedance, you can put the fault impedance. If not, then just put a fault, put a short circuit, and then do your calculation for the positive sequence circuit. That is balanced faults. Unbalanced faults, you have to figure out how to connect the circuits. Single line to ground fault, they were all in series, and the sum of the voltages were equal to the fault impedance. Now this is a line to line fault. Line to line fault, they tell you that I0 is equal to 0. So I0 is equal to 0. What is V0 going to equal? If I0 is equal to 0, V0 is also equal to 0. So this circuit will not exist. I don't care about this. It will just be an open circuit. It will be left as an open circuit without any current flowing through it. Yeah. So it will not be connected. Then they tell you that these 2 circuits, the positive and negative sequence circuits, have opposite and equal currents. And they also tell you that, so this is my V1 and this is my V2. They tell you that the difference between V1 and V2 is placed across the fault impedance. So maybe I can draw it this way. Take my positive sequence circuit. This is V1, right? This is my negative sequence circuit. This is V2, right? Current I2 is here, current I1 is here, right? So if this is V1 and V2, right? They're telling me that V1 minus V2 is placed across the fault impedance. So if I place the fault impedance here, ZF, then does it have V1 minus V2 across it or not? It does. It has V1 minus V2 across it. And the current I1 and the current I2 are opposite and equal. This condition. Right? So the current I1 here and the current I2, which is the negative sequence current, they are equal because it's a series circuit, but they just have opposite polarities. So this would be the sequence circuit for a line-to-line fault. Okay, so the zero sequence circuit is out in space. There, we don't care about the zero sequence circuit. So any questions about this? So then the example, they're not going to repeat what the first step. The first step is always take your system and find your sequence circuit representation, positive, negative, and 0. Go to the point where you have a fault, at bus 2 in this case. It's the same. The fault is always at bus 2 in the same system up here. The same system that we looked at last time, whom we drew a sequence representation for, is this. It's the same system. right? So we started with this system, our basic system. This is the basic system. We took the system and drew the full positive, positive, negative, and zero sequence circuits. We went to bus 2 here, bus 2 here, and bus 2 here, and found the Thevenin equivalent circuits as seen from bus 2. We drew our 3 Thevenin equivalent circuits in sequence domain. And then, depending on the type of fault, you connect. Right? So depending on the type of fault, we will figure out how to connect. We figured out how to connect a single line to ground, and now we figured out how to connect the line-to-line faults. So for the line-to-line faults, as I said, we connect them the way we just drew them. So how do you, if you want to look at an example, again, you can look at it quickly. Again, we have the same voltages, same impedances in the sequence circuits that we originally had. We just need to connect them in a different way, depending on the type of fault. So now, if I want to calculate the current in this circuit, what is the current in this circuit equal to? This voltage divided by these impedances. Like this voltage, the current I1 or the current negative I2, since they are opposite of each other, is equal to the voltage divided by the impedance. The I0 is equal to 0. Then what? The subtransient, remember, phase A current is equal to 0. The fault is on phases B and C. So I take my positive sequence current. It's equal to, if I go back to the relationship between phase B and the positive sequence current. So IB and IC are negative and equal to each other. So if I would like to calculate my phase B current, right? If I have my sequence current, how do I calculate my phase current? Here. My sequence current, given my sequence current, right, we can always go from sequence to phase, phase to sequence, by either using the sequence matrix or the inverse of the sequence matrix. Yeah. So here they did that for you. So if the phase B sequence current is equal to I0 plus A squared I1 plus AI2. So we know that I0 is equal to 0, since this is a line-to-line fault, and then we can find IB from A squared I1 plus AI2. And I1 and I2 are equal to each other, but opposite in sign. So they found IB from I1 and I2. Okay. And this will be the A minus A squared or something. This is the minus J squared to 3 is this A minus A squared here. Is this A squared minus A. Will be the minus J squared to 3 here. Minus J squared of 3. Okay? So you have your sequence currents, and you went from your sequence currents to the phase currents by using the inverse of the sequence matrix. And then they had, okay, this is still in per unit. They also asked you for actual value. So you need to go and back to chapter 3 material, look at the base value of current in that zone. Multiply the per unit value by the base value, which was 4.183 in this case. So you calculated the actual values of the current in this case. What else do they want? Calculate the subtransient fault current per unit and in kiloamp for a bolted line fault from phase B to phase C. I don't know what this is. I think this is a typo. Because yeah, the phase B current is equal to, I think this is phase A current. Yeah, I think they're referring, here phase A current is equal to 0. Calculate subtransient fault current in per unit for a bolted line-to-line fault from phases B to phase C. Yeah, this is phase A current, it's equal to 0. Phase B current is equal to this, phase C current is equal to the negative of this. Right? The line-to-line to ground fault is the last one. So line-to-line to ground, what are the conditions that I have? I have 2 lines, line to line to ground fault. So these are my 3 phases. the two lines are touching each other and they are touching the ground. Right? So I can put a ZF here, and this is phase A, phase B, and phase C. Right? So my conditions are the following. Phase A, IA is equal to 0. IB plus IC is what's going to be flowing in the fault impedance, right? So the current will flow from IB plus IC. They will flow to the fault impedance into the ground and back to the neutral of the star, for example, right? So IB plus IC multiplied by Z fault is equal to either the VBG or VCG, because VB and VBG and VCG will be the same. They will be equal to the current flowing in the fault impedance multiplied by the fault impedance value. So the voltage drop across the fault impedance. So these are the conditions. IA is equal to 0. VB is equal to VC, right? They're touching each other. VB will be equal to VC. They're just touching exactly equal to each other. And then VB or VC are equal to the current flowing in the fault impedance multiplied by the value of the impedance. So these are my input conditions. Again, I will take my input conditions, manipulate them using the sequence identities that we talked about. The outcome will be a set of conditions that we have here. Okay? What do these conditions tell us? I0 plus I1 plus I2 is equal to 0. So I will have, again, you start by drawing your sequence circuits. 0. Positive and negative. So these are my sequence circuits. This is V0 plus minus V1 plus minus V2. This is I0, I1, I2. These are your circuits. They're telling you that I0 plus I1 plus I2 are equal to 0. They're also telling you that V1 is equal to V2. So if I1 plus I0 plus I1 plus I2 are equal to 0, what does this ring? Does this ring any bell from your circuit analysis? They are balanced. That's what else? Oh, what else? From circuit analysis, what else? What else can you deduce? What happens? Let's say if I have 3 currents coming into a node. Kirchhoff current law. What does Kirchhoff current law say? That whatever current, any current coming into the node is equal to current coming out of the node. So if I have I0 and I1 and I2 coming into a node and nothing coming out, so it means that I0 plus I1 plus I2 is equal to 0. Right? So which means that okay, fine, they're balanced. Right? So, but from Kirchhoff current law, I'm trying to figure out how to connect them together. To connect the circuits together. These are conditions that are sort of going to help me connect the circuits. So how can I make use of this? I can make use of this by saying that fine. This means that it seems like these nodes will all be connected to each other. These nodes where I0 is coming in here, I1 is coming in here, I2 is coming in here. These nodes will all be connected to each other. So I can draw the connection, but I will redraw it differently. But now I know that I can draw the connection between these nodes here. This satisfies this top one, right? Also, V2 equals to V1. So I can do what else? The positives are already connected. All the positives are already connected. Yeah, I can connect the bottom node of the positive and negative sequence circuits together as well. Right? Right? I can connect, since V1 is equal to V2, I connected their positive terminals and I connected their negative terminals. So V1 is equal to V2. Right? And then V0 minus V1, and then V1 is equal to V2, right? So V0 minus V1 or V0 minus V2 is equal to 3ZF times I0. So I have a voltage across a fault impedance that has a zero sequence current flowing through it equal to V0 minus V1. So I have what? This is V0, right? It's connected to the top here, they're connected to each other. Right? So how do I connect this one? Let me redraw so that it's easier to visualize. Okay, so this is my positive sequence circuit. I know that my positive sequence circuit, V1, my positive sequence voltage, my negative sequence voltage are equal. So I can draw a positive sequence voltage and negative sequence voltage in parallel, right? So how about I do this, for example? So this will be V2, right? So positive sequence voltage, negative sequence voltage are equal. And then V1, V0 minus V1 is equal to 3ZF times I0. So this is V1, right? Between these two nodes I have V1. And this is V0, right? And this is I0. So I can put my fault impedance here. And this is 3ZF, right? 3ZF is with current I0 flowing through it, right? Has what voltages across it? V1 on this side and V0 on this side. So V0 minus V1 is equals to 3ZF times I0. I0 is flowing this way, right? So from circuit analysis, the voltage across this impedance, if the current is flowing in this way, it's V0 minus V1. Okay? So this is how you would connect the sequence circuits in this case. Let's look at the... So this is what we just drew, right? Any questions on this? And then it's circuit analysis, right? And then it's finished. I mean, it's you want to find your positive sequence current. How do you find your positive sequence current? You group these two impedance. You group the impedances here and take this voltage divided by the impedances, and then you have to use Kirchhoff current divider, current divider rule to figure out the currents flowing in these branches versus the current flowing coming in. Right? It becomes a circuit, but you just have to make sure that you pay attention to your variables and the way that their polarities, so that when you find the current flowing, and if it's going in this direction, then this current is equal to negative I0, right? So just make sure you maintain the polarities of the sequence variables, the sequence quantities. You have to make sure that you maintain their polarities. So, and then this is an example with some numbers. So they want to calculate the subtransient fault current in each phase, the neutral fault current. Neutral fault current is equal to what? So since this is a double line to ground fault, there will always be a zero sequence current, right? The zero sequence current is equal to 3 times the neutral current, right? The neutral current, remember, the phase currents are all flowing in the neutral. The phase currents are all flowing in the neutral, and the phase current zero sequence quantities are all equal. So 3 times I0 is what's flowing into the neutral, right? It's only the zero sequence quantities of the phase current that's flowing in the neutral, because the positive sequence and negative sequence quantities are balanced quantities. So they will sum to 0 at the start point. And what is left? What is left will be the zero sequence quantities of the phase currents. I0 of phase A, I0 of phase B, I0 of phase C. So what is the neutral current? The neutral current is equal to 3 times I0. Because I0 phase A, I0 phase B, I0 phase C. Remember, the zero sequence quantities are equal in magnitude and phase. They're all in phase. And then the trick here is that the contribution to the fault current from the motor, this is the trick, okay? This is the pretty tricky part, because now you have to work your way backwards. Here they tell you what are the contributions to the fault current from the motor and from the transmission line. It is not clear from here. Here what you will do is you will find your sequence quantities, right? But how do you find the contribution of the motor? right? They're trying to find the contribution of the fault current from the motor and from the transmission line. What is the contribution of the motor to the fault? And what is the contribution of the transmission line to the fault? Where is the transmission line here? It's not clear, right? So you will actually have to go back and go back to your previous circuit. So let's think they draw it or no, they don't draw it. But we'll have to go back and look at it, yeah. So we go back and look at our original circuit. Let's go back here. This is our original circuit, right? Our original circuit had a motor here and a transmission line here. They're telling you what is the contribution of the transmission line to the fault at bus 2. And what is the contribution? So we have the fault at bus 2, current, because we can, fine, we took our circuit, we converted it to sequence circuits. We found our Thevenin equivalent at bus 2. From the Thevenin equivalent at the bus 2, we saw, okay, they say the double line to ground fault. So we connected it in a certain way. Connected it in a certain way, and then what did we do? Calculate the sequence voltages and currents from circuit analysis. And then, knowing your sequence currents and voltages, you can take those and convert them to phase quantities. So you know everything about the fault current at the bus. So you know the fault current. Right? You know the fault current at the bus. You know the positive sequence fault current, negative sequence fault current, and zero sequence fault. You know the fault current values, right? Because you will be able to calculate I0, I1, and I2 from the connection circuits that we came up with. So you know I0, I1, and I2, right? This I0, the zero sequence fault current at bus 2 is going to be flowing in here, right? It's going to be flowing in the zero sequence circuit between bus 2 and ground. Right? Do we agree or no? No? Okay, do you see the, okay, do you remember, this is the representation of this system. Do we agree with that? We did this 2 lectures ago. Okay, so we took this system, we have the generator, we took the generator, again, it's a generator with a star connection bolted to ground without an impedance to ground, right? So there will be zero sequence current flowing, so it's a impedance with a short circuit. And this was a delta star transformer. Delta, there will be no zero sequence current flowing, so it's an open circuit on the delta side. On the star side, the star with a connection to ground, bolted impedance connection to ground, so there will be a connection, a short circuit here. You go back to the representation of the transformer. Then there is the transformer impedance and the transmission line impedance. Transformer impedance, transmission line impedance. And then there is another transformer coming that we see here. This transformer is star with a bolted neutral on one side. So the zero sequence current can flow into the star through the ground and back through this star's ground. Right? So there has to be a capability for zero sequence current to flow, since I have a star grounded here, star grounded here, right? Any zero sequence current will be able to flow between the two grounded connections of the star. So then I have an impedance and then a short circuit to ground. So impedance, short circuit to ground. And then I have a delta here. Delta does not allow zero sequence current to flow out. So it's an open circuit on the delta side, open circuit on the delta side, right? Then the motor is a load. It's an induction motor. They didn't say it's a very high power motor. They didn't say that you can need to consider its fault value, fault voltage. So in the zero sequence circuit, sorry, they didn't say anything about the zero sequence representation, because the zero sequence representation will only depend on the neutral, what's connected between the neutral and the ground. Between the neutral and the ground, I have a fault impedance. This fault impedance, they gave you the value of it, right? That's 3 times Zn. So we have an impedance of the motor, x0, which is 0.1, and then 3 times Zn, representing this motor in zero sequence. So it's 3 times Zn, or 3 times xn, and then the 0.1 that I have for the impedance of the motor. That's my zero sequence representation. The positive sequence representation, I guess they did say that the motor has sufficient. You reduce the sequence network to the Thevenin equivalent as viewed from bus 2. Pre-fault voltage is blah blah blah. So I will be more clear, because here they don't say that there is the pre-fault voltage on the motor. They say the pre-fault voltage in general, right? So pre-fault voltage is the voltage basically in the positive sequence. It's 1.05 on the generator, but they need to be clear that there will be a pre-fault voltage on the motor side, because remember, if you go back to the induction motor representation in the sequence quantities, we can put they said, okay, if you go back to that, that's the previous chapter. So if you go back to that, they would say that you can or cannot. So you may or may not use a voltage source in the positive sequence circuit, depending on. No, we didn't. There was in the previous chapter. You may or may not use a voltage in the positive sequence circuit, depending on the motor rating. But I will be clear the problem right here. It was a bit unclear. But they tell you it's a big 100 MVA motor, so the assumption is there is a pre-fault voltage. So they put a voltage source in the positive sequence circuit as well. So all of this, these are the separate representations for the sequence circuits. Right? What we did was consider the fault conditions. In the fault conditions, these sequence circuits are actually connected. So we took these circuits and we did what? We came up with their Thevenin equivalents. We came up with zero sequence, Thevenin equivalent. Positive sequence, Thevenin equivalent. Negative sequence, Thevenin equivalent. Where? At bus 2. This is bus 2. This point is this point. And this point is this point. Okay, so again, this point is this point here. So I've come up with the Thevenin equivalent circuit for the circuits between these two nodes. And then what will I do? Then I have to go and check out what the fault is. The fault will decide how I connect these up, right? But at the end of the day, I will be able to find what? I0, I1, and I2. Right? These are the positive, negative, and zero sequence currents. Where? Here. And going into this fault. Right? So this is zero sequence current. This is my positive sequence current. This is my negative sequence current. This positive, negative, and zero sequence currents that I've calculated from these circuits, I've calculated them here, right? This is what I've calculated from these circuits. Regardless, you connect them whatever, depending on the fault. Connect them. Put some connection here between them. I don't care. Connect them and find the values of V0, V1, V2, I1, I0, I1, and I2. Connect them and find the values. How you connect them, depending on the type of fault. Then you find their values. These values are where? They're actually physical quantities of, they're actually currents that you can plug in, that they're going to be flowing from this node into the fault, right? So there is a contribution from the transmission line. This is the transmission line, right? This is the transmission line. This is the transmission line. And this is the motor. This is the motor. This is the motor. Right? So, is the transmission line contributing to the zero sequence current for a fault at bus 2? No, don't look at me. Look at them. Is the transmission line, again, as I said, you have the positive, negative, and zero sequence circuits. Okay? These are the Thevenin equivalents at bus 2, for example, right? Then I told you there is a certain type of fault, so you connected them in a certain way. I don't care which type of fault. Whatever type of fault, you connected it in a certain way, and from the connection you were able to, again, it's voltage divided by the impedances, and you were able to find the currents. I0, I1, I2, and V0, V1, and V2, or the voltages here. Right? We only have 6 quantities of interest. Right? So you found these quantities, right? Where do these quantities actually physically go on the original representation of the system in sequence quantities? They go here. So the current is actually going to be the zero sequence current at bus 2 due to the type of fault. So this is my bus 2. There is a zero sequence current between this bus, this node, and my ground. Right? There is a sequence, zero sequence that you've calculated. You've calculated that zero sequence current because remember, I've connected these circuits somehow. I'm not going to draw the connections between these circuits because the connection between these circuits is this thing here. It was used to calculate the current flowing from this node out from this node. Current going out of this node. Current flowing out of this node into the ground. Right? That's what this was used for. Now this current is here. I'm telling you that this current, this exists. There is current flowing out of this node. Okay, we've calculated that. If you've calculated that, then this current is going to come in this circuit. Where is it going to come from? Can it come from this side? It cannot. It's an open circuit on this side. So if I ask you what is the transmission line's contribution to the zero sequence current, in this case it's 0. But what is the motor's contribution to the zero sequence current? It's the full zero sequence current. All the zero sequence current is coming from the motor. But how about the positive sequence? What is the transmission line's contribution to the positive sequence current? Oh, now you have to current divider rule. You have a circuit. This is current flowing in here. How do you divide up the current between this current? You know this value. You know this value of current. So how do you know what value of current is coming from here and from here?
Figure out the current on the motors.
It would be current divider rule. I mean, the voltages they're equal, so as if they don't exist, right? The voltages are equal and opposite in magnitude, opposite in polarity. So the voltages will as if they don't exist. If the voltages don't exist, then you have a current here and an impedance on this side and an impedance on this side. So this current is equal to the full current multiplied by the ratio of the two impedances, this impedance over this impedance. And if you want to find this current, it's the full current multiplied by the ratio of the two impedances, this impedance over this impedance. Right? Current divider rule. And here it's the same. If I want to find the contribution of the transmission line to the negative sequence current, it's also, I have my negative sequence current here. I have my negative sequence current. Let me canvas, white background. I have an impedance here. I have an impedance here, and I'm telling you this is my positive sequence current. This is I transmission line. This is I motor. How do you find I transmission line? This is given. And this is given. Z transmission line is given. And Z motor is given. You know this impedance and you know this impedance. And you know this value of current. So what is IM? I1 times current divider rule, guys. It's one of the impedances, right? It's over the sum of the two. Yeah. So Z transmission line over Z transmission line plus Z motor. I believe she is correct. So we go back. I mean, the solution is there. So thankfully we can review our current divider rule by looking at the solution. No, these are different examples, right? So this is the solution is, we did the double line to ground fault, right? And then after the double line to ground fault, there was this example. This is where we are, right? So our example is the most difficult one is this part. So the subtransient fault current in each phase. This is no problem, right? You find your positive, negative, and zero. So you have your circuit. You can solve this circuit easily and find positive, negative, and zero sequence currents, positive, negative, and zero sequence voltage. Now you have your positive, negative, zero sequence voltage. They're telling you what is the subtransient fault current in each phase. They're asking for the phase values of the fault currents. So you take your sequence currents, convert them to phase quantities, right? And then the neutral fault current. Neutral fault current, you know that 3 times the zero sequence current is equal to the neutral fault current. So you've calculated your zero sequence current here from this circuit. Take that, multiply by 3. The only difficult part is this last one. Okay? When they tell you the contribution to the fault from the motor and from the transmission line. And here they make it a bit easy for you by saying neglect the delta star transformer phase shifts, because otherwise it becomes a nightmare. Right? So that's where you have to go back to the original circuit and use the current divider rule. Really, I mean, that's really the most difficult part to all of this, is you have to go back and look at your original system and apply the current divider rule. So let's see how they did it here. So first we calculated we looked at our circuit. We want to calculate I1. How do you calculate I1? I1 is this voltage divided by the parallel combination of these two impedances plus this series impedance, right? That's how you calculate I1. So that's what they have here. It's the voltage divided by the parallel combination of the impedances plus that series impedance. So they found I1. If you find I1 using current divider rule, if you have I1 here, how do you find I0 and I2? So I2 is equal to I1 multiplied by the opposite impedance over the sum of the two impedances. Correct. So here, just to confirm, so I2, which is the current in this branch, is equal to I1, which is the which is the J4.5 blah blah blah, and they use the minus sign. They flip the sign because I2 is going up. The assumption is I2 is going up, so they flip the sign here. So it's J4 blah 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 multiplied by 0.25, which is the opposite impedance, over the sum of the two impedances. Opposite impedance is 0.25 over the sum of the two impedances, right? And then this is the zero sequence current. So now I have positive, negative, and zero sequence currents in my circuits. I can take these, positive, negative, and zero, and convert them to phase quantities, right? So they took them, positive, negative, and zero, converted them to phase quantities using the sequence matrix that we've talked about before. And this is the resulting, these are the resulting phase quantities. We expect that phase A is equal to 0, phase A current is equal to 0, because this is a double line to ground fault. We said that phase A is open, phase B and C are connected and touching each other, and then there's impedance between them and ground. So we expect phase A current is 0, and that's what we ended up with. A is 0, and then these two, we expected them to be, some values, and they ended up being, equal values, but different in phase. It makes some sense because I have voltage sources on phase B and C. Now I'm connecting them both together, so the currents, but then they're both seeing the same impedance, right? So they're both seeing the same fault impedance. So the current magnitude may be the same, but the phase shift was different. And this is what happened here. So, and here they took, so this was in per unit, and then, knowing your base, you can convert that to actual values as well. Right? The neutral current we said is equal to 3 times the zero sequence current. So the zero sequence current we had was here, J1.6734. So I can take that, multiply by 3, then multiply by my base value, right? So the 3 times I0, and then I took that, multiplied by my base value to find the actual values. Okay? Now is the tricky part. The tricky part is what we discussed. Okay, so what is the contribution of the motor to the zero sequence current? What is the contribution of the motor to the positive sequence current? What is the contribution of the motor to the negative sequence current? That's where we did the current divider rule that we did. The motor's contribution, the transmission line's contribution to the zero sequence current is 0. The motor's contribution to the zero sequence current is all the zero sequence current, and that's why we took the zero sequence current here, which we calculated, J1.6734, and that was the motor's contribution to the zero sequence current. Right? So here we go back to our original system. We had some zero sequence current, again, flowing out of this node into the fault, right? From this node into the fault. This is my zero sequence current. where is it coming from? It's coming only from this side. So all of the zero sequence current is coming from the motor. Nothing is coming from the transmission line. Now the positive sequence. I have a positive sequence current out of this node into the fault. This is coming partly from here and partly from here. How do you find that? Current divider rule. Same thing here, negative sequence current. Negative sequence current is coming out of this node into the fault. It's coming partly from here and partly from here. So we have to do the current divider rule. And that's what they did here on this last slide of the example. So they said, they did it for the zero sequence current, motor transmission line. Positive sequence current, motor transmission line. It's equal to the positive sequence current. The line's contribution is equal to the positive sequence current multiplied by one of the impedances, the opposite impedance, over the sum of the impedances. Right? And then here, same thing. This is for the line and for the motor. For the motor, it's equal to, the motor current is equal to, the motor's contribution to the positive sequence current is equal to the positive sequence current multiplied by the opposite impedance over the sum of the two impedances. Right? So that's the current divider. Same thing here for the negative sequence. Exactly same. They take it's equal to the transmission line's contribution to the negative sequence is equal to the negative sequence current multiplied by the opposite impedance over both. Is it okay? Is it clear what we did? This is just nothing but current divider rule. Right? So what do they do next? Yeah, they take these. So these are what? These are all in sequence quantities. So if I want my motor's phase current, right? I cannot take my sequence current that I calculated originally. I have to take my motor's sequence currents and then convert them to phase. Right? So here, I think that's what they did here. They took they did it for the line and the motor. They took the sequence currents here. They took the sequence currents in the lines, sequence contributions from the motor, converted them to phase. Right? So if you do it wrong initially, this will also be wrong. So these come from the current divider rule. Right? These vectors come from the current divider rule. Okay? So any questions on this? Is it a lot of circuits? It's 214, really. It's lots of 214 material. Yeah. On steroids, really. So really, this wraps up what I want to discuss in chapter 9 on symmetrical faults. I will not cover the sequence bus impedance matrices, and this is the last thing in the set of slides. So this just talks more about power. Power world is capable of doing everything we did. So you can build your power world example, and it will calculate the three-phase balance faults, or will calculate single line to ground, double line to ground, or line to line. You just tell power world, there's a fault at this bus, and they will tell you, okay, choose what type of fault, and they will do the same calculation. So it's what you're learning is really how people build something like power world. That's what we did here. We're learning here. So I will, this wraps up chapter 9. I will, try to discuss chapter 10, just overview. Okay, I will not. So I assigned some homework problems. You have chapter 7, 8, and 9. Okay, and they're all 7, 8, and 9 are all interlinked, and they're the same. Really, you have a system, and it's basically the same as what we did today. You have a system. Take your system, draw your positive, negative, and zero sequence representations. You are told, for example, there's a fault at bus 1 or 2. You go to that bus. You find the Thevenin equivalent at the bus. You draw your 3 sequence circuits. Then you're given the type of fault. Type of fault will mean a certain connection. There will be 3 types of faults, plus the balanced fault, of course. The balanced fault, you only solve the positive sequence. The other 3 types of faults, you connect them according to what we discussed today. There were 3 types of connections. They're on your equation sheet, and they're drawn for you on the equation sheet. So you connect them. After you connect them, you calculate the positive, negative, and zero sequence voltages and currents. So these will be the fault, the positive, negative, zero sequence fault currents. Then if I tell you, then you can take those and convert them to phase quantities if I'm asking for the fault current. Or if you're trying to buy a circuit breaker or a fuse and you're trying to find the fault current that this circuit breaker or fuse has to withstand, right, or break. So, but if then you have to protect the specific pieces of equipment as well. So you protected, the fault current, you want to find the piece of the fuse at that specific breaker, for example. But you also want to find what is the fault current contribution of the other pieces of equipment when a fault happens here, because you may want to protect them in a different way. So then you have to go and do the current, go back to, take your I0, I1, and I2 that you've calculated, go back to your original sequence representation, and then use the current divider rule to find the contribution from both sides. And then this will be the contribution from each piece of equipment. That's really chapter 7, 8, and 9. Yeah, this last assignment includes 7, 8, 9. Yeah, I mean, chapter 7 is really, okay, it's do single phase equivalent circuit analysis. I mean, they're just telling, but they also include a lot of work on selecting fuses and circuit breakers. We didn't have time to do that. I mean, I skipped that part. I mean, it's really, it's you take your, there's a peak value of current, there's the, you have to calculate your subtransient current and steady state fault current. And then you will use these two values to select circuit breakers and fuses. That's a summary of that, okay? So I skipped that section, but read it. I mean, it's a selection of equipment sort of material. It's interesting. I think you should read it, okay? But to produce the theory, I think I had to, skim through. But chapter 7 is really, okay, balanced faults. Balanced faults mean only positive sequence. So you do everything we're doing here. I mean, in the assignment that I gave you for chapter 8 and 9, there's, they tell you, okay, this is the system. What is the current for? What's the fault current for a balanced fault? What's the fault current for single line to ground fault? What's the fault current for double line to ground fault? It covers all of the 7, 8, and 9. Yeah. So you will have to do all three. I mean, all three are very interlinked. Yeah. Again, I wish we had more time to cover all of chapter 10 in a lot of detail. I will not be here next Monday, so this is the last class basically. So I will just briefly talk about protection. So I think you realize now that there's fault current. When there's a fault, current increases. Right? That's something that happens. If current increases and you have impedances on the way, what does that mean for voltage at the fault versus the voltage before the fault? If there's impedances on the way and current is increasing, means that there's a voltage drop. So by the time you get from the source to the fault, there's a high fault current, there are impedances on the way, so the voltage at the fault will definitely be lower than the voltage at the source, right? So we only really have two things to play with. We are seeing drops in voltage, and we are seeing increases in current. These are the only two things we have to play with during a fault. Right? So these are the main things. We can look at frequency and how that affects, but we don't get into that even in this chapter. But generally, these are the two main things. So, and how do I measure drops in voltage and increases in current? By a current transducer. And the fancy name for it is a current transformer in power systems. Or a voltage transducer or sensor. The fancy name for it is a potential transformer. Right? So that's the fancy name for the voltage sensor and the current sensor that we use in a power system. Of course, the design of those is very specific. I mean, you have to make sure that if it's a sensor, when you design any sensor, you want to make sure that whatever quantity you are sensing, you are really taking that quantity into your protection system or your brain, the protection controller, exactly as it is. Right? You want to make sure that that sensor is not overloading or changing or modifying that signal. So if I'm measuring a current using a transformer, this transformer, remember, has a magnetizing branch, has losses, right? So you want to make sure that you account for that in your protection system design. And this chapter talks a little bit about that. So we don't have too much time, but the idea is, okay, you will have to make sure that you're replicating your current and you're replicating your voltage properly. And this is by proper design of the CT and PT, or the current transformer and the voltage transformer. Right? We don't get into the design of those, but we can select them. And when you select them, they will tell you, okay, the excitation current is this much. Right? It's a transformer, right? Since remember, these are very high voltages and currents. For me to measure very high voltages and currents, I want to step them down to something reasonable so that I can measure them. So what's the best way to step down AC voltages and currents? A transformer. I can use a voltage divider, right? You can use a resistive voltage divider or a capacitive voltage divider. You can, right? But then you end up with no isolation, right? You end up with no isolation. Let's say you have a voltage here, 10,000 volts. You have a voltage between these two nodes equal to 10 kV, right? AC. I can use this R1, R2 I can make this R2 5 volts, right? You can or no? You can. You can select R1, R2 to be. But what happens if this R1 burns? What do I get on my computer here? 10 kilovolts, right? Huh? No. If R1 is a short circuit, burns. It's burned. Becomes a short circuit, for example, right? This wire, touches this wire. Something happens here. Then you get 10,000 volts on your computer or the whatever instrument the person is touching, right? That's why transformers are great, because fine, I can put a transformer like this, and I can have here up to 5 volts from 10 kV, right? If you do that, and you touch here, no problem, right? If there's a fault on the primary on this side, this winding touches this winding or whatever, then I don't care. Nothing. I mean, I will maximum see 5 volts here. As long as I can maximum see 10 kilovolts here on this winding, I will maximum see 5 volts on this side. Right? So that's why we have transformers. I mean, before people are able to come close to the electrical network, the utility makes sure there are transformers, isolating transformers. Because if there is a fault, and for some reason these two touch each other, right? Then what? If there's a fault on the primary side, and for some reason these two touch each other, or there's no isolation, meaning there's no isolation, then what happens? Same problem, right? This thing is touching 10 kV. Right? That's why transformers are beautiful. They're very nice because they isolate. They save us, right? It's a nice way to save humans. Otherwise, we will have a lot more people dying from electricity. So that's why we can use these resistive voltage dividers. We can use capacitive voltage dividers. So there are some capacitive voltage dividers used as PTs, voltage transformers, or potential. They're called VTs or PTs, voltage transformers or potential transformers. But the most common is the transformer based, not the capacitor based, mainly for safety reasons. Because where are these located? They're not going to be located in your house, right? In your house, you typically will have fuses or miniature breakers, miniature circuit breakers. So typically, actually, what we have in Qatar is the substation that is outside your compound or outside your neighborhood will have a transformer. And this transformer is then, let's say connected to, let's say it's single phase, and it's connected to many homes. This is your home, her home, other person's home. And typically what we do here in Qatar is the outgoing of the transformers will have fuses. And the incomings of the transformers will have circuit breakers. Right? So fuses are devices that fuse will just burn if the current flowing through it is higher than a certain value for a certain period of time. Okay, breakers are mechanical devices. They do not open by themselves. Breakers are just switches. The breaker needs a sensor connected in the system, for example here, and this sensor has to be connected to what is called a relay. This is not what you've heard before about relays. Relays that you've heard about before maybe are just as electronics. If you played with electronics, you have a small box here with a contact that you put, you put 5 volts across a winding, for example, and then this contact opens and closes. This is called this is a small electronics relay. Relay in a power system terminology is only the brain. It's the brain of the power system protection system. The brain of the power system protection design. It requires a sensor to be interfaced to it, CT or PT, current transformer or potential transformer. So you have to have sensors. These sensors are going to be connected to relays, and these relays will then control the breakers. They will have current coming out of the relay and then exciting the breaker. Okay, turn on, turn off, giving the breaker a signal. So the breakers are dumb devices. They do not open by themselves. They do not sense. The breakers do not sense, because the breaker is something that it's a switch. If I want to protect a transformer, I have to place the sensors in a different, a certain way. If I want to protect these loads, I will have to put the sensors. If I want to protect this load, it's different than if I want to protect all of these loads together, right? But I can have this CT and this CT go to the same relay. And this relay can be controlling one breaker out here, right? So not every breaker will have a single relay. So there may be several, we'll have several single CT or a PT. There may be several CTs or PTs. So the way you design the protection system is depending on what equipment you have and how you want to protect them. And we will look briefly at that, very briefly. I don't think we will not have time here. But the idea is for a protection system to work, you have to have a CT or a PT connected to a relay. And this relay is what talks to the breaker, open and close. Right? So these are the three components of a protection system. Chapter 10 is about, okay, where do you put these CTs and PTs? Do you put the CT here? How about if I'm measuring, let's say I want to protect this load. One idea is I can put a current transformer here, and then this current transformer is connected to a relay. This relay is then connected to a breaker that is here, and it tells this breaker to turn on or turn off. Right? That's one way. How about if that's if the source is here, for example. But what if, for example, I have a source here, another source, somehow. Like let's say you have a renewable energy system on your rooftop, and you're also connected to the grid, right? You took 489, right? You can have these online grid-tied converters here. So you have these two sources now in your system, right? How do you protect your system this way? So maybe you need another CT here, right? So if you put a CT here, you want, let's say, okay, that's a good point. If I keep a CT here, if I keep a CT here, right, and I see an increase in. Actually, if I put the CT here originally, forget about this one. If I put this CT originally, I put it here. And as soon as I see an increase in current, I disconnect, okay? This will disconnect what? The grid. But this will not see fault currents coming from your PV system, right? So a better place to put the CT would not be here, would probably be right here, right? So where you place the CT is important, right? And then, of course, I cannot only put a breaker here, because if I put the breaker here, and let's say there's a fault, right here. No, the fault happens here. It doesn't happen in this line. It happens right before this line somehow. Right? Somebody, two wires touch each other here before your actual feeding or before your actual load. There's no problem with the load. There's a problem with the cable connected from the grid to the load. So the fault happens here. If the fault happens here, so what's going to happen? This CT will see a high current. If this CT sees a high current, then this breaker can open. Okay? If I don't put the CT here and I put the CT here, what's going to happen? This CT will see nothing. Do you agree? If the fault is here, if the fault is happening here, where is the high current? High current is coming from the source into the fault. Right? This is where the fault is. I'm assuming I don't have a PV system yet. If I don't have a PV system, then the fault current will flow from the source into the fault here. Right? So in this case, if I have my CT over here, is this CT going to see a high current? It will not. So we originally said that this is a good place to put the CT. Right? But now I'm saying if the fault happens here, this is not a good place to put the CT. Right? So maybe you need another CT here. Right? So where you place these CTs, the current transformers, will depend on where the fault current is coming from, the fault current contribution. That's where this, fault current contribution is an important consideration. After you calculate the fault current, okay, where is this fault current coming from? So because this will help you define where you put the specific CTs. Okay, if I want to I'll have to stop. Yeah. Yeah, we will stop. I mean, again, the protection chapter. The protection, by the way, is very nice, very interesting, but it has a lot of conceptual stuff. So it's a lot of, okay, if I put it here, what happens? If I put it here, what happens? But it's not just conceptual, because you have to go back to your sequence circuits, see where the fault current is coming from, and then decide based on, okay, where is the equipment? Where is the fault current coming from? Do I have one source or two sources? If I have two sources feeding my system, do I want to disconnect the load, even though there's a fault only close to one of the sources? No, you don't want to disconnect the load. You want to disconnect the specific source only. So you have to be discriminating between your loads and sources so that you are able to maintain as much of the system working as possible, right? So if people say, if the utility says, okay, there's a fault somewhere, let's turn off all of the power in Doha, right? Doesn't make sense, right? So the protection system has to be very selective. The very selective, we just saw in the simple example, means that maybe I have to have 3 CTs in a simple example like this. So I measure current coming from this source, current coming from this source, current flowing into the load, right? 3 CTs just for a small single load example, right? So how much protection devices do I put, right? Protection, again, you can put so much. You can invest a lot in protection, and in this case, your system will be very well protected, but very expensive to protect, right? And this is okay if the loads are very critical. If the loads are nothing but your house and my house, what we do in Doha is a fuse at the output of the transformer for the outgoing loads, the residential loads, just a fuse. If I want to be more selective, because that means if your house has a problem, I lose my power too, right? But they're okay with that. For residential loads, it's okay, it's no problem. But if I don't just use a fuse coming on the feeder that's feeding all of these houses, I use a fuse on the input of every home. Then what happens? Then if one home has a problem, that home goes out of the system. But I'm left with the rest of the homes powered, right? So, but in this case, what did I have to do? I had to use a lot more protection devices, right? So how much protection devices and sensors do you put in the system is what a protection engineer has to deal with, right? So how much and where? How much and where? And then how do you coordinate those, okay? Coordinate means, okay, let's look just quickly at this and then we'll stop. Do I want, let's say, this is typical characteristic of a relay or a fuse. Canvas, desktop background. If I have a system that looks like this, a source, bus bar, bus bar, bus bar, load, 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 right? So let's say a fault happens here. How is the fault current going to flow? It's going to flow from here, from the source. What does the fault current see? The fault current sees this impedance, this impedance, this impedance, all the way to here, right? If the fault happens here versus at point 1 versus at point 2, which will see higher fault current? Fault current at 1 will be higher, or fault current at 2 will be higher? Fault current at 1 will be higher, right? Because it's seeing less impedance on the way to the fault. So fault current at 1 will be higher than 2. But what if? So I want 1. So 1 will see higher fault current. So if it's higher fault current, do you want it to disconnect faster or slower? If it's high fault current, you would like to disconnect it fast, right? I mean, that's ideally you would like, as soon as I see a fault current, disconnect, right? Here I have a breaker, for example. Open up this breaker. That's what you would like to see. But so let's say the fault happens at 2. If the fault happens at 2, we said that at 2 I would see less fault current because of these impedances in the path. So I would put a device. So let's say the fault current is 2 amps. So let's say it's 2 amps, for example. If the fault current is 2 amps, I want to make sure I disconnect in, let's say this is seconds. This is 0.9 seconds, for example. This is how fast I can disconnect. This is this relay's capability. This relay offers you these curves. These curves you choose the one curve that you operate on, And how do you choose? There's two settings. It's called the current tap setting, or current rating of the basically of the relay, and then the time dial setting. It chooses these curves, 0.5, 1, 2, 3. This is called the time dial setting. There are two settings, and these are typical mechanical relays. Current tap setting and time dial setting. So current tap setting is multiples. It's you choose it at 1. 1 means, and here relay input current in multiples of current tap setting. So if the relay input current is 5 amps and your current tap setting is 1, that means I have 1 amp coming in, 5 amps coming in. This is in multiples of current tap setting. So 2 times my current tap setting is 1, for example, is the relay coming into the current. 2 times 1 is 1. Is 2, sorry. So if I have 2 amps coming into the relay and I've chosen the current tap setting to be 1, then 2 amps would refer to 2 times the current tap setting. So it's 2 amps in this case coming into the relay. Regardless, okay, the idea is each relay, mechanical relay or correspondingly digital relay can be designed in the same way, will give you a set of curves, operating characteristics. You choose the one operating characteristics. How do you choose this or this or this or this? For example, if I have a fault at 2 and I say I want to disconnect as fast as possible for a fault at 2, then I will choose this fault current is 2 amps. Let's say this is this is in amps. So 2 amps is my fault current. How fast will this relay disconnect at 2 amps? In 0.9 seconds or 0.8 seconds, whatever time is here, right? How about a fault that happens here? A fault that happens here will have higher current, right? If it will have higher current, let's say 3, does it make sense to choose this same relay characteristic? Maybe, right? If a fault current happens, and if I put this relay, I choose the same relay characteristics and I put it at this, protecting this bus, then what happens? Then for a fault at this point 3, this will disconnect at 0.5, for example, seconds, correct? But what if, so this will disconnect very fast, right? It's a higher current, it will disconnect fast. It makes sense. If I put, choose the same characteristic, you operate the relay with the same characteristic, but at a different bus. How about if a fault happens at 2? If the fault happens at 2, and the relay that is protecting bus 2 fails, right? If it fails, right? What do you want to happen? What would you like to see? I would like to see that relay at bus 3 will disconnect, right? If the relay that's connecting fault at bus 2 fails, does not operate, then I would like to make sure the relay that's protecting this bus picks up the slack. It's a backup for the other relay. If it's a backup for the other relay, and the fault is here, so the current that's operating is here. This is the current that's operating. If this is the current that's operating, then it will disconnect at 0.9 seconds, right? If the current is higher, it will disconnect at if the current is higher, if the current is lower, sorry. So this relay here at bus, I think we need to stop. The idea is these relays. Let's say these relays have to back up each other. That's the main idea. If I have a radial system, this is called a radial system. I have a source here, right? And faults can occur here on this bus, here on this bus, here on this bus, here on this bus. I can have a sensor here, a sensor here, a sensor here, and a sensor here, for example.
So do we have a lab for that?
No lab. Or you're supposed to, but I don't know if you will do it or not. You did it?
We did like numbers one. We didn't understand anything.
Okay.
It's
So
just like a thing that
keeps beeping. Okay. So I think since it just keeps beeping, we'll have to stop here. The idea is, okay, you design these protection systems so that you make them work as fast as possible, but you also make them back up each other. So this will operate the fastest. You want to make sure that this will operate fast for a higher value of current, but if the value of current is lower, meaning this failed, and the fault is here, so the fault current is lower, you want to operate this. For the lower value of fault current, you want to operate this greater period slower. You want to operate it slower. So for example, you would choose maybe one relay to work on this characteristic, one relay to work on this characteristic, one relay to work on this characteristic, right? So meaning if the fault current is 2, this will disconnect first, right? If the fault current is still 2, meaning the fault is at this last bus, do I want the relay before it to disconnect? If I chose the same characteristic at the same value of fault current, it will also disconnect. No? Yes? If two relays, okay, if two relays be after each other, right? This one, there's one here, and there's one here. The fault is happening on this bus. Okay, the fault is happening on this bus. For a fault current on this bus, fault current is 2 amps, for example, because remember, this is the larger impedance. If the fault happens on this bus, the fault current is 3 amps. Okay? If a fault current is 2 amps, it means that the fault is happening here. Do we agree? The fault is happening here. Who do I want to disconnect first? The breaker here. Because if I disconnect the breaker here, I've disconnected more loads. So I want this breaker to disconnect first. But what if it doesn't work? I want the one before it to disconnect. Do I want it to disconnect at the same time exactly? Or I want it to back up this last relay because it didn't operate properly. So I want it to back it up. Back up means it happens after it, right? If it fails, the current will persist. The fault current will persist in the circuit. But this is lower fault current than this one is set to disconnect at. This is set to disconnect at 3 amps very quickly. This one is set to disconnect at 2 amps very quickly, right? But if the fault current is 2 amps, meaning the fault is at the end, and this breaker does not work, the relay does not work, something happens, this is not functioning, I want to make sure that this backs it up. Well, what is the fault current? 3 amps or 2 amps in this case? 2 amps because the fault is at the end. So what do I want this to do when the fault current is 2 amps? Do I want it to disconnect as fast as possible? No, I want it to be a backup for this one. So I have to make it delayed. So it makes sense then that this last relay operate the fastest at 2 amps. The one right backing it up will operate also at 2 amps, but in a longer period of time. Let's say the one here can back up these two and operate even after that for a fault current of 2 amps. But for a higher fault current, a fault current here would be, let's say, 5 amps. For the higher fault current, this relay here will operate also in a short period of time. Right? You see the benefits of, so this is called coordination. You put relays or fuses or breakers and you coordinate them. Right? So you have to coordinate them because one has to back up the other, one has to back up the other in the radial system. But there's a big problem. If you have a very long radial system, then you end up with, let's say there's a fault at the end, and for some reason all of these breakers fail before you. Then there's the problem, right? I mean, then you will choose what? You will choose the highest characteristic. Then the fault current will remain for 10 seconds, 15 seconds, because you go higher and higher, the duration is longer, right? Doesn't make sense sometimes to do that. So there's a limit to how many relays can back up each other in a radial system. Right? I will stop here. I mean, protection is very nice, but there's a lot of this kind of stuff. You look at these diagrams, you look at where the current sensor is located, and then you have to choose the proper characteristics of the relay or the fuse or the breaker. And you have, for example, you have some a more complicated. So we looked at a simple coordination exercise now, yeah. But you have a much more complicated exercise. For example, here, they show you fuses with breakers, and so they have a system here, composed of these are different houses, for example, and this is a recloser and this is a breaker. So they use 3 protection devices. They use some fuses here. They use a recloser, which is a device that opens and closes multiple times, and then it locks out at some point. And then they use a breaker. So you can have multiple kinds of protection devices. How do you want to coordinate these? You want to make sure that what? These are fuses. The example we discussed, we want to, okay, there's a fault happening at this load. I would like to make sure that, maybe this fault is not permanent. Maybe somebody just stuck a pen here and then got electrocuted and fell off, and then everything is fine, right? You don't want to disconnect the whole house in that case, right? Doesn't make sense. So maybe have a recloser here. A recloser is a device that can sense fault current and open, but then will close back again. Because if it's a temporary fault, it will go away. If it's a tree, fell on a line, this tree got burned and then fell on the ground. You don't want to disconnect the neighborhood, right? So in that case, the recloser will sense that fault current, open up temporarily, and then close back again. It's called a recloser. So the recloser, you want it to operate, be the fastest thing to respond. But then you're not going to reopen and reclose 100 times, because then somebody will be cooking, right? So, but if you open and reclose, maybe you open, reclose again one time, very fast, and then open again, but reclose after a longer duration. And then if you open and reclose again and the fault persists, it means, okay, don't open and reclose again. Khalas, there's a serious fault, okay? So then you leave it to the fuse maybe. Then you leave it to the fuse. You allow the fuse to, okay, maybe there's a fault here that's permanent. The fuse here will burn and disconnect. You don't want the breaker to respond at that moment. You prefer to have, okay, recloser act first, see if it's a permanent or temporary fault, and then have the fuse, okay, if it's a permanent fault, okay, recloser don't open, remain closed, but have the fuse, see the load and open up, and then, okay, if that's the case, if this fuse does not, if there's still a fault, have the circuit breaker respond and open up the full system, right? So several layers. So in this case, it's a much more complicated system. I will have the reclosers see a value of current and disconnect. They will disconnect the fastest. These are the recloser curves, very fast. Then, depending on the logic that you've designed, then I left the fuses curve. Any current here will then be seen by the fuses first. These are the fuse curves, right? And then I have the overcurrent relays, the phase overcurrent relays all the way back here. These are the circuit breakers. This is the last thing I want to open. The last thing I want to open is the circuit breakers. The ground overcurrent relay, remember, if we go through your problems in chapter 9, you will see that the single phase fault will have lower fault current than the three-phase fault. It's a lower value of fault current. So typically the way you would sense a single phase fault is you look at, there will always be a zero sequence current, right? For a ground fault with a ground connection, there will always be a zero sequence fault. Zero sequence current flowing, meaning current flowing through the neutral. So the way you would detect that, because it's a lower current, if you're going to look at a high value of current, like a three-phase fault current, then you're not going to detect the lower value of current. So the best way to detect a fault with a ground loop connection is to look at the zero sequence current, or the neutral current. So that's why they have that ground fault, the ground overcurrent relay happening before the phase overcurrent relay, because phase overcurrent relay would look at a higher value of fault current due to maybe a three-phase balance fault. But you still, if the recloser stuff doesn't work, the fuse stuff doesn't work, then you would maybe it's a single line to ground or a double line to ground fault. And the way you detect that is first using the ground overcurrent relay. If the current is even higher than that, you want to detect that using, if there's no zero sequence current, that means the fault is a three-phase fault, right? Or a line-to-line fault. You want to detect that using the phase measurement. So you put a phase overcurrent relay. So this is where, okay, I had to put a current sensor on the neutral. I had to put the current sensor on the phases. How many do I have to put on the phases? All three or two, right? So this is protection, okay? I mean, you have to plug numbers to this, of course, right? But do you see what this is talking about? At least briefly. I mean, why this is below this, why this is below this. It's because this is how I want the physical system to operate. I would like the recloser to test the system first. Then, if it doesn't work, I would like the fuses to act. If the fuses don't work, that means maybe the fault is closer to the breaker, right? So if the fault is closer to the breaker, is it a single line to ground fault? Yes, you look at the phase ground neutral current first. If it's high, disconnect. If it's not high, then you leave it to the phase current measurements. Okay, if there's a high phase current, there's no neutral current. That means it's a three-phase fault close to the source, right? So this is how you coordinate a system like this. I will stop. I promise.